Hi guys, this is Bio2365, and as usual in biochemistry we are doing something new. Now this will be our first video tutorial ever, and we're going to be looking at buffer calculations. This is going to be very helpful for your second assignment, which will be solely based on pH and buffer calculations. So I am hoping that this will help you a lot. As usual, this was done entirely for your benefit, so please send me your likes, your dislikes about it, how we can improve this service for you all. Alright, so let's get started. Alright, so buffer calculations. So for those who don't know me as yet, that's Jason Matthews' name. And I recommend that you all get on board on Facebook. Right, you can do so by doing a search for BiochemGM. I think it'll be very useful in that it's a very easy way to interact with me, as well as you get all the notices and so on about whatever files I'm posting up and so on. So I look forward to seeing you all there. Now, a typical calculation, or what they would probably do, is give you a K value and ask you to calculate pK. Now, first thing you need to remember is that pK is equal to minus log K. Now, there are many times in the exam room that the student, it's not because they don't know the chemistry or the biochemistry behind it. It's because sometimes they can't use their calculator. I hope that won't be the case here. So you press minus log 1.7 on the calculator. And I think that's fairly straightforward. I think the next one is where some people go wrong. And you should look for that exp button on your calculator. It's exponent. And that simply means by 10 to the power of whatever number you're going to type next. Alright, because some people they would use there's a y to the power x button on the calculator. That's going to give you a wrong answer. You need to use the exp button. And then you type to the power, whatever power it is, which in this case is -5. And when you press the equal sign, you're going to get the correct pK value. Now here are 3 typical questions that I normally bring for the exam. And unfortunately, some students would try to use the Henderson-Hasselbalch equation to answer each one. I will tell you that that's not the case here. Alright, you cannot use the Henderson-Hasselbalch equation to answer all 3. In fact, it might just be one of them you have to use the Henderson-Hasselbalch equation. Alright, another thing is that I gave you the pK value, but that doesn't mean that you should try to use the pK value for all 3 parts. It could simply mean that it is needed for one part. So when you reach this part of the presentation, I would recommend that you pause the presentation now and you go and you try these questions on your own and see what you come up with, because in the subsequent slides I will be answering each one of these questions, and you can see if your answer matches up to the answer that I got and the way how I did things. Alright, so please take a few minutes, go get your paper, get your calculators, and try these questions on your own and see what you will come up with. So I'll see you back in a few minutes. Alright, so the first question is, what is the pH of the following solution? 50 ml of 0.2 molar HCl plus 50 ml of 0.1 molar NaOH. So the first question you have to ask yourself is this a buffer system? And you should remember from your previous lecture that buffers contain either a weak acid and its conjugate base, or a weak base and its conjugate acid. In this system here, we have neither a weak base or a weak acid. HCl is a strong acid and NaOH is a strong base. Now, if you have a mixture of strong acid with strong base, if you have the equal number of moles of H plus and OH minus, you're going to get the resulting pH to be 7. So the question now is in this system, is there the same number of moles of H plus as there OH minus? And the answer is no. They may have similar volumes, and you might be tempted to say yes, they have equal moles of H plus and OH minus. But if you look carefully, they have different concentrations. The HCl concentration is 0.2 molar and the NaOH concentration is 0.1 molar. So all of that is same volumes. Because their concentrations are different, they're going to have different number of moles of H plus and different number of moles of OH minus. So the pH will not be 7. Alright, so there are some questions you need to ask yourself. You need to find out which one is in excess. Find the pH using the relevant formula. If you look at the previous lectures, there was a certain slide where we listed all the different formulas and so on. Right? You need to choose the correct one. And when you're using this question for this answer, you need to also consider the final volume because you'll be dealing with concentrations. Now the answer for this question is 1.30. And if you look, you will see that the pH is 1.30, and I put it to 2 decimal places. And for your answers, when you're giving a pH, you should always state your pH to 2 decimal places. So I'm hoping that the pH 1.30 is what you got. If not, well then go back and see if you did these things. Find out which one is in excess and use the right formula. Alright? So this is the typical answer for this question. Now, if you watch, first we say, well, how many moles of HCl is in the 50 mils, and then we find out how many moles of NaOH there is in the 50 mils of that solution. You're going to get the information here. 0.2 molar HCl. Now, 0.2 molar means that that in 1,000 mils, there will be 0.2 moles HCl. So if 1,000 mils contains 0.2 moles HCl, then 50 mils will contain 50 times 0.2 divided by 1,000, and you get 0.01 moles HCl. You do the same thing for the NaOH. The only difference here is that the NaOH is 0.1 molar. So 0.1 molar means that in 1,000 mils, there will be 0.1 moles NaOH. So therefore, in 50 mils, there will be 50 multiplied by 0.1 divided by 1,000. So you get 0.005 moles NaOH. Now, for every 1 mole of HCl, it's going to react with 1 mole of NaOH. So if you look here, 0.005 moles NaOH is going to react with 0.005 moles HCl. But you don't have 0.005 moles HCl. In fact, you have more than that. And you have an excess, in fact, of 0.01 minus 0.005 to give you 0.005 moles HCl. Now, the formula you're going to be eventually using is pH is equal to minus log the concentration of H plus. Remember, these square brackets means concentration. So it means that if it's a concentration, you need to find out the volume component. Now, we already found out how much moles of H plus, because for every 1 mole of HCl, there will be 1 mole of H plus. So if you have 0.005 moles HCl, it means that you're going to have 0.005 moles H plus. The total volume would have been the 50 mils at the beginning plus this next 50 mils. So you get 100 mils. Now in concentration, the volume is in liters. Now to convert mils to liters, you simply divide by 1,000. So that's why you get 100 divided by 1,000 to give you 0.1 liters. So you bring those two pieces of information here together, and you see that we get 0.005 divided by 0.1 to give you 0.05. Now, what I should have here is mole per dm cubed. So I should write, so please, when you are doing your calculations, please write this in moles per dm cubed. And you just simply substitute here and you get the answer to be 1.30. The second question asks you, if you combine 20 mils of 0.1 molar acetic acid plus 50 mils of 0.1 molar NaOH, what would be the resultant pH? So we know that a buffer consists of a weak acid and its conjugate base. The question here now, is that the situation here? And the answer is no. Yes, acetic acid is a weak acid. And when you combine acetic acid to NaOH, you get sodium acetate, which is its conjugate base. But in this question here, the resultant solution must have a weak acid and a conjugate base. And if you look carefully, all the acetic acid will react in this thing. So again, you're doing something similar to the first one. You're going to find which one is in excess, and you find the pH using the relevant formulae, alright? And you have to again consider the final volume. The pH for this question would have been 12.63. So again, pause the presentation here. If you got 12.63, well, great, you can continue. If not, see if you got the correct one in excess and see if you use the right formula. And if not, well, then we go to this next slide here. So you see again, we're going to be doing something similar to what we did to the first question, which is we're going to find out how much moles of acid and base are in the respective volumes. So again, you're going to be using this 0.1 molar, and 0.1 molar means that in 1,000 mils it contains 0.1 moles. So for the first one, 1,000 mils contains 0.1 moles acetic acid. Alright, so then 20 mils will contain 0.002 moles acetic acid. 1,000 mils contains 0.1 moles NaOH, 50 mils will contain 0.005 moles NaOH. So the one that is in excess, and again the NaOH and the acetic acid is going to react in a 1-to-1 ratio. In this case, you see that if they're reacting in a 1-to-1 ratio, then 0.002 moles acetic acid is going to react with 0.002 moles NaOH. We have more than 0.002 moles NaOH. In fact, we have an excess of 0.003 moles NaOH. And again, we need to find the total volume of the solution. We added 20 mils to 50 mils, so the final volume would have been 70 mils. We're going to convert the mils to liters, so we get 0.07 liters. So again, the concentration of OH minus in this case is the number of moles of OH minus, which is 0.003, divided by the total volume, which is 0.07 liters. And this answer, as with any other concentration, will be mole per dm cube. And I did not write the units here, so please, for your question, you write the answer there. Now that you have the concentration of the OH minus ions, there are two steps involved. Alright, and two different formulas you have to use before you get to the pH. So first of all, if we know the OH concentration of OH minus, we could find POH. And POH is simply minus log of the concentration of OH minus. So we get a value of 1.37. The other formula you're going to be using is pKw is equal to pH plus POH. Now at 25 degrees Celsius, pKw is equal to 14. So if you substitute 14 and you substitute 1.37 as the pOH value, and you make pH the subject of the formula, you get an answer of 12.63. And now we come to the final part C, and that is if we have 50 mils of 0.1 molar acetic acid and 20 mils of 0.1 molar NaOH, alright, what would be the resultant pH? Is the resulting mixture a buffer? The answer is yes. The final mixture will contain both acetic acid, which will be its weak acid, and it will also have its conjugate base, which is sodium acetate. In this question, in this part, we would need to use the Henderson-Hasselbalch equation. Alright, you need to calculate how much acetic acid we need final mixture, and when you substitute these values into the Henderson-Hasselbalch equation, you should get a pH of 4.68. Remember, the pK value was given at the beginning. Alright, so we will first find out the acetic acid. We will find out how much moles NaOH are in the 20 mils, and you should be able to know this by now. Alright, and if 0.002 moles NaOH reacts with 0.002 moles acetic acid, then you're going to be left with 0.003 moles acetic acid. Alright, so you go use the Henderson-Hasselbalch equation, and if you look carefully, I always state my formula before I substitute my values, and that should be your practice as well, because the formula carries a mark by itself. So please state your formulas before you go and you enter the respective values. So pH is equal to pK plus a log of the concentration of the conjugate base, all over the concentration of the weak acid. Alright, so the 4.86 was given in the question, and the A minus will be your conjugate base, which is sodium acetate 0.002, and your weak acid would have been the excess acid that did not react, which is 0.003. And if you plug in those values, you should get a pH of 4.68. So a buffer requires two components, a conjugate base and a conjugate acid. So one of the typical buffers in a lab is the tris buffer. Now, they could give you one component. So for instance, if they give you tris base in the lab, then you have to add acid to get the acid component. If they give you tris HCl is provided in the lab, then you add base to get the tris base component, because you must always have a conjugate base component and a conjugate acid component. Now, in the previous lecture, we looked at good buffers, and examples of good buffers were MOPS and HEPs, and these are what we call zwitterionic buffers. So if they tell you that they give you in the lab the zwitterionic form of the buffer, then you need to add base. If they give you the anionic form, you need to add acid. All right. Now, if you're a little rusty about tris and zwitterionic, I will recommend that you go back to the first lecture where this is discussed in more detail. Other traps in buffer calculation that it could give you is that in your preparation, you have to be careful about what kind of acid they give you. If they give you HCl, remember that 1 mole of acid will give 1 mole of H+, because it's a monoprotic acid. But if they give you an acid such as H2SO4, well, that's a diprotic acid. So it means that for every 1 mole of H2SO4, you're going to get 2 moles of H+. So be very careful about the acid that they give you. You must ask yourself, is it a monoprotic? Is it diprotic? Because then the volumes will be different. So this is an example of a typical exam question once again. And there's a lot of information there, and you have to train yourself in to be able to pull out the relevant information and use it to suit. So the first thing you should do is find out the mass of tris base required. Now, how are you going to do that? You need to pull out the relevant information to find out the mass of tris base required. And that is it there. You have 1 liter of 0.1 molar tris, and they give you that the molecular weight is 121.13 grams per mole. Alright? So if you look at the question here, the answer here, right, 0.1 molar means that in 1 liter there's 0.1 moles of tris. For this question, the required volume is 1 liter. Therefore, 0.1 moles of tris is required. Now, if I had asked, for instance, that I wanted 3 liters, then you would have multiplied 3 by 0.1 to get that number of moles that was required in that volume, right? So be careful, because in your question, it mightn't be simply 1 liter. It could be 2 liters, 6 liters, 0.5 liters, you know? So be careful that you will have to multiply that number of liters by the number of moles to find out your total number of moles. Now that you know that you need 0.1 moles, then you could convert that to a mass, because you know from your molecular weight that 1 mole of tris has a mass of 121.13 grams. Therefore, 0.1 moles will be 0.1 multiplied by 121.13 divided by 1, so you get 12.113 grams. The second step that you're going to do is use the Henderson-Hasselbalch equation, because you want to find the ratio of conjugate base to conjugate acid. You're going to do that by finding the pH value as well as the pK value. And you're just going to simply substitute that into the Henderson-Hasselbalch equation. Again, please, for these calculations, state the Henderson-Hasselbalch equation, because you're going to get 1 mark there. Now, be very careful when you reach down here, because a lot of students have trouble finding the anti-log. So it's not a problem of chemistry or biochemistry, but it's more a problem that they can't use a calculator. So I ask you to please go back and learn how to find anti-log on your calculator. Now the ratio of A minus to HA, concentration A minus to HA, is 0.126. Alright, and that can be simply said as 0.126 over 1. So you need to decide whether it's an acid or base and how much. Now remember from the previous slide, you need to see what they gave you. They gave you tris base. So try to remember now, if in the lab they give you tris base, how do you make the buffer? What do you add? Do you add acid or do you add base? Because if you see here, they didn't ease you up. They give you both 1 molar HCl and 1 molar anyway. So you have to try to figure out now which one you're going to use. Alright? So a buffer requires an acid component and a base component. If the tris base is given, then that means you have the base component. You need to get the acid component. The only way you can get the acid component is if you add acid to the base. Alright? So from the previous step that we discussed, we got the ratio of A minus to HA to be 0.126 over 1. So now we need to calculate what is the concentration of acid that we need. Now the numerator represents A minus and the denominator represents HA. So it's a matter of maths now and ratios and so on. It will be 1 divided by the total. So you're going to add these two numbers. So if you say I put 1 over 1 plus 0.126, and all of that we multiply by the total number of moles of buffer, which you found was up here was 0.1. So you get 0.0888 moles. So in these cases, you know, a little number of significance, like 4 significant values would be good. So if you watch here, because the tris buffer must have tris base and tris HCl. They gave you only tris base, so you're going to make the amount of tris HCl that you need. Now you need, how much is tris HCl? You need 0.0888. You need around 0.088 moles tris HCl. Now 1 mole of HCl is going to react with 1 mole of tris base to give you 1 mole of tris HCl. So if you need 0.0888 moles of tris HCl, it means that you will have to react 0.088 moles HCl with 0.088 moles tris base. So the HCl is in a 1 molar concentration. So if 1 mole HCl is in 1,000 mils, you need to find out how much 0.8, well, this should be this is a little error here, it should be 0.088 moles of HCl, so that'll be 0.088 by 1,000. So you get 89 mils, and it's very hard to get 88.8 moles, so we just round it off to 89 mils HCl. Alright, so that 89 mils HCl produces 0.088 moles tris HCl. I mean, tris HCl in terms of the Henderson-Hasselbalch equation will be your HA. Now, finally, you're going to bring all the information together. So you're going to dissolve 12.113 grams tris base in 89 mils of 1 molar HCl and bring the solution. You see, I say bring. Students tend to know, like, alright, it's 89 mils HCl. So they minus 89 from 1 liter and actually put a numerical value for the distilled water. That is incorrect, because what will happen is that this mass of tris base is going to add to this volume. So the volume is no longer 89 mils. It's going to be more than 89 mils. So you make up the final volume to 1 liter. Alright? And you use distilled water. So that's how you're going to finalize your answer. So if you bring everything together now, this, for a question like what is there about tris base, this is your typical answer. This is how it's going to be, it should be formatted. Alright? Now, for your practical this week, you also have to prepare a buffer, and they give you a variety of choices. Alright? And you have to prepare 100 mils of 0.1 molar buffer at pH 7.6. First, and you're supposed to do these calculations before you go into the lab. So first, find the total number of moles of buffer in 100 mils. Alright, and you have the concentration as 0.1 molar. So you should be able by now to find how much moles will be in 100 mils. Alright, Then ask yourself, what are the two components of a buffer? You must have a weak acid and a conjugate base, or you should have a weak base and a conjugate acid. So use the Henderson-Hasselbalch equation to find the ratio of each component. Now that you have these two pieces of information, you can work out the number of moles of each component, alright? And then convert the moles into masses, right? Now, most people might go with the, I believe it's phosphate salts or some sodium salts that they give you. You might be tempted to go with that. There's also one way you could use a synthetic amine, and that one is more challenging, and I challenge you all to try that one. Remember, you have the NH2 and you have the protonated form NH3+. So what you have to ask yourself, will the NH2 be the acid component or the base component? And if you have NH2, how do you go to NH? How do you go to the protonated form? And that's the clue there is it's in a you need to go to a protonated form. So if you want to protonate something, would you add acid or would you add base? So I'll leave that up to you to try to sort out. So good luck with that. Tell me how the lab went. Alright, so guys, once again, I hope you learned something. Please give me feedback and best of luck with your studies. Alright.